Okay, everybody, so today's video is on the trapezoidal rule, and probably I'll make a separate video for something else called the Simpson's rule. Okay, in the assignment they're probably all lumped together, but I'm going to make separate videos on them, and then once you get a handle on the videos you could try the assignments, or you can try the assignments first or whatever, but it's all going to be in the video. Okay, so the trapezoidal rule is something that we use as a way to estimate a definite integral. So suppose that we want to evaluate this definite integral for some reason. Definite integrals can be lots of things, all right? Depending on what you do. If you're a certain kind of engineer, or you study the sciences, say like physics, then definite integrals can do lots of things for you. All right, but so suppose you want to evaluate that, and maybe we don't have complete information here. Like we might not know that function. You know, you get the impression when you do problems in math books that the function's always nice and clean and you know every number, but maybe you don't in reality know that. Maybe you can just measure some things about it or something like that. You might not have an equation for that function f of x, okay? So in those cases, perhaps the best you could do is to estimate the integral. So as far as maybe look at the big picture, for integrals, there are things called analytical methods, all right? That's something like, say, if you use the fundamental theorem of calculus and you say, well, here's how you work the integral. You find the antiderivative of this function, f of x, and you evaluate it between the bounds a and b according to the fundamental theorem of calculus, okay? In contrast to that, there are things called numerical methods, all right? The trapezoidal rule gives us an estimate that's considered a numerical method. Like say where instead of using like an antiderivative, which is a definite formula, we'll calculate an estimation to this based on a finite number of sample points or measurements or something like that. Okay, so maybe you could use information obtained from a laboratory to estimate that integral. All right. So now that's the big picture. I haven't told you how to do this yet, and I'm not quite there yet, but I'm getting there. All right. So just hang in there. I need, rather than just cut to the chase constantly and tell you how to do stuff, I need to give you a little background information. And it's nice, I think, also if I can give you a way to understand what's happening. All right. So let me talk for a minute about how to understand the trapezoidal rule, rather than just tell you how to do it. I mean, it'd be nice to understand it too, in my opinion. So you can think of this definite integral from a to b f of x dx. One way you can think about it that's pretty natural, and it's visual for all of you visual thinkers out there. You could think of that as the area under this curve. So suppose that curve right there is this function f of x. Then one way to think about the definite integral is that's the measurement of this area right there. So if you could calculate this definite integral and you get a number, that would be the physical size of this shaded region. Okay? So therefore, as a result, we can estimate the integral by estimating the area under the curve, all right? Since they're the same thing, since the integral and the area under the curve are the same thing, if we could estimate the area under the curve, that would serve as an estimation to the integral. All right, now, let's say like here in my picture, I've drawn the same curve to the same scale and all that. One way that works pretty well that we could estimate the area there is to inscribe 4 trapezoids of equal width. And you might not see it. The trapezoids fit the contour of the curve so well that you might not be able to see where they are. I've drawn them in red ink, but for example, this is a trapezoid, okay? And yes, they fit the contour of the curve very well. Not perfectly, you see a little bit of over measurement right there, but they fit it very well. So Maybe when you took Calculus 1, you learned about Riemann sums that involved inscribing rectangles on the curve, and the rectangles are kind of coarse and they don't fit so well. The trapezoids fit a lot better, it turns out. All right. So suppose I do that. I put 4 trapezoids in there with equal width. Then it turns out that if I could just find the grand total area of those 4 trapezoids, that would be what we call T4, the trapezoidal rule with 4 trapezoids. That definite integral would be roughly equal to the grand total area of the 4 trapezoids that you see in that picture, okay? And that's all the trapezoidal rule is. Really, that's it, okay? Now, in the context of doing some problems, we'll need to refine this process, but if that makes sense to you, then I think you understand the trapezoidal rule. So let's see like how you do this in practice, okay? What are the steps? So we start with a definite integral, naturally, because the trapezoidal rule provides an estimation to a definite integral, okay? Next is we decide how many trapezoids to use, or say that might be given to you, all right? Maybe the problem says use the trapezoidal rule with 5 trapezoids or something like that, whatever. And we'll let that number be n, okay? And then the width of each trapezoid. Remember in my picture I showed you just a minute ago, I said that, well, we'll take this space and we'll put 4 trapezoids of equal width, all right? So the width of the trapezoid will be the upper limit of integration minus the lower limit of integration divided by n, where n's the number of trapezoids that you're going to use. Okay, so say you get that number. Next, we need to come up with this thing we call partition. We'll partition the interval a to b. A is the lower limit of integration, b is the upper limit. So here's what we do. We count from a to b by the width of the trapezoids. Okay? That's it. So you find the width, you start with number a. We'll call that actually x sub 0 in our partition. We add that width to that number, and we get the next one, and we get the next one, all the way through. Okay? And there will be n plus 1 numbers in your partition. All right. And then, all right, so here's the formula. Tn, the trapezoidal rule based on n trapezoids, will be b minus a. Remember, b is the upper, a is the lower limit of integration, over 2n times this quantity. We take the partition elements, we put them into the function that's given in the definite integral to start with. We double all calculations except for the first one and the last one. And we add out all the results together. So it's like f of x 0 plus 2 times f of x1 plus 2 times f. And we double all of them. And then when we get to the last one, very last number there, xn, we put that in. We don't double that one. We add them all together, multiplied by b minus a over 2n. That's the trapezoidal estimate, all right? And yes, the definite integral is roughly equal to the trapezoidal estimate. Okay. All right, so those are the steps. We got the steps laid out. Let's see if we can do a problem. How about 2 problems based on that? Okay, so I give you a definite integral. I'd like to calculate this one, since that's doable there, the exact value and the trapezoidal estimate. Okay, so we'll calculate the exact value because we know it should be doable this time. And I thought just to practice T4, and for the sake of comparison, we'll calculate that too. Okay? All right, so exact value of this thing. Definite integral 1 to 2, 1 over x dx. Okay? So let's see. How do you do this analytically? We need the antiderivative. All right, natural log of x. And we evaluate between bounds. We'll get natural log of 2 minus natural log of 1. But natural log of 1 is just 0, so this will just turn out to be natural log of 2. And that would be an exact answer to our definite integral, but I'll go ahead and round it because we're going to want to compare with the trapezoidal estimate anyway. So we'll get 0.6931. So, okay, about 0.6931. Okay, so that's how you calculate the exact value. The exact value is actually natural log of 2, okay? What about T4? All right, so I'm going to go through those steps that I outlined in the previous slide, okay? So, first of all, I'll give you the trapezoidal width. And I said that that was b minus a over n. And my upper and lower limits of integration are 2 and 1. And then we're going to calculate T4, so that means 4 trapezoids. So that's going to be 1/4 or 0.25. Okay. So that is how I get the partition. So how did I say you get the partition? We count from 1 to 2 by 0.25. So the partition is like so. Start with 1. Okay. Next number, 1.25. Okay, we'll keep counting by this much. 1.5. Okay, keep counting until you get to 2. 1.75. Not quite there yet. Keep counting. 2. All right. And then there are 4 trapezoids. There should be 5 elements in my partition, and there is. Okay. All right. So here goes. T4 is going to be, what was that formula? B minus A over 2n. Like so. And then this. All right. So I'm going to get 2 minus 1 over 2 times 4. All right. Now, it said, if I can summarize the way I would read this, put all my partition elements into my function that was in the definite integral and double all of them except for the first one and the last one. So I'm going to get, so what was my function? It was 1 over x. So I'm going to get 1 over 1 plus 2 times 1 over, what's the next number? 1.25 plus the next number, 2 over 1.5, where this is what I'm getting when I plug the partition elements into that function. F of x is 1 over x. Okay, so keep going. 2 times 1 over 1.75. And now I'm to the last one right there. 2 is the last element of my partition. And so I just need to do 1 over 2. So I put every single element of my partition into my function, and I doubled all of them except for the first one and the last one, and that's what I said that you would need to do. All right. Now, if I calculate this, then I'll get, like, so I'll double all of these, you know, add 1/2 and 1, and then that turns out to be an 1/8, and I'll put all that together, and it turns out to be about 0.69, so 0.6970, okay, if I do four spaces. All right, so that's what I'll get out of this. How does that compare to the exact value? That's pretty close, okay? I mean, I think it makes sense it would be pretty close. Just generally, you could see, you know, with my other slide, you could see how well the trapezoids fit the contour of the curve, and, you know, so I can't be real surprised. I can't say, of course, in every problem we're going to be this close. It depends on how curved the curve is and so on, but yeah, it's a pretty good estimate. All right. Okay, so we got that. We're in good shape there. Let's try one more with a function that's it just looks a tad more complicated. Okay. All right. So here I was wondering about giving the exact value. Okay. All right. And then again, calculating the trapezoidal rule with 4 trapezoids. Okay. All right. So how do we get the exact value? With some analytical method. Okay. And that would require finding the antiderivative of this with those limits. That's what the fundamental theorem of calculus is. All right. Now, we could get this antiderivative by u substitution. And at this point, we've done a lot of u substitution. All right. Okay. So let me just tell you, just because we've done so much u substitution, I mean, I guess it doesn't hurt to practice more, but if I'm going to make the point of my video the trapezoidal rule, then I'll try to just keep it at that. So let's see, we'll get 1/3 x squared plus 3. That power's a half, so we'll get 3/2 here for the power. Okay, and then we'll have from 0 to 5. And then with the 5, we'll get, let's see, this is not going to be a nice number, I can say, but 28 to the 3/2 power over 3 minus, and then with 0, we'll get 3 to the 3/2 power over 3. And so there's your exact value, all right? Like no rounding, it's perfect. No decimal places left off or anything like that. But I am going to want to compare with the trapezoidal estimate. So I will round this, and you'll get 47.655. Okay, just 3 places. That's what you're going to get. All right. So I know if I boxed that, that's not technically that's not the exact value, but I wrote the exact value right there. Okay. T4. Let's try T4. Okay. So what was the procedure for the trapezoidal rule? I find the trap width, find out how wide each trapezoid is, and that would be the upper limit of integration minus the lower over the number of trapezoids we're going to use, just like so, and we'll get 1.25. All right, that's how we count from the lower limit of integration up to the upper limit of integration, one at a time, to get our partition. All right, so our partition, and I don't know if I said it earlier, but you know, the partition is like, you know, going from here to here to here to here to here. The partition is where the trapezoids would stand if you were looking at a geometric picture. All right, if you were seeing it that way, that's what it would be. All right, so the partition. So we'll start at the lower limit of integration, which is 0. We'll count by this until we get the upper limit of integration, which is 5. So we'll get 1.25 after that. Then if we keep counting, we'll get 2.5. Okay. And then if we keep counting, we'll get 3.75. And we're just trying to get up to 5. Up, and then the next one, if I take 3.75 plus 1.25, I get to 5. The partition should have one more element than the number of trapezoids you're using. So T4 is the trapezoidal rule with 4 trapezoids. Sure enough, I have 5 elements in my partition. Okay. All right, so here's what T4 is. T4 is, what was that formula? Upper limit of integration minus lower limit of integration over 2 times the number of trapezoids you're using. And then in here, we put every element of our partition into this function given in the original integral. We double all but the first entry and the last one. So let's see, if our function's x times root x squared plus 3, then I'll get 0 times root 3. That's what you get if you put 0 in there. Okay. And then we need to do 2 times 1.25 root 1.25 squared plus 3, right? I gotta double that one, and I put 1.25 in like so. All right. So it's gonna be no fun to write all this out, but that's the way it goes. So then 2.5 root 2.5 squared plus 3. Okay, plus, keep going. Now I'm at the 3.75. I'm still doubling. So 3.75 root 3.75 squared plus 3. Okay, and I got one more. I'm gonna have to like continue this line right there. So that last number would be 5. I'm not gonna double that one because I'm doubling only the ones except for the first and the last. So I'll get 5 root 5 squared plus 3. Okay. All right, and then I'll do the math on all that. Before I do that though, just keep in mind that, you know, just so you don't get lost in all the numbers, that the function that we use is the one that was given in the original definite integral. X root x squared plus 3, right? Okay, and that's what all these are based on, except for the doubling is built into the trapezoidal rule formula. Now, so if we do all this, right, and multiply by 5/8, which is what that number is going to be, then that turns out to give us this, T4. Well, before I do it, it's going to be, we expect something fairly close to that, right? That's the way that it works. It's an estimate to this number. So when we do this, it turns out to be 48.740 to 3 places. So yes, it's close. It's not dead on accurate, but it's close, right? That's the way an estimate works. It turns out the more trapezoids you use, the bigger that number is, the more accurate this will be. So you could get like whatever desired amount of accuracy you want just by increasing the number of trapezoids. Nonetheless though, look at that. See that thing right there? Look at this. Look at this procedure. Those are these steps with that formula. Okay?